Hi, my name is Sarah, and this summer I've been working on using LiDAR data to classify forest disturbance in California. So first, a little bit of background on forest disturbance and forest structure. The main types of disturbance that California sees are climate stress, biotic agents, human disturbance, and wildfire. And then a really big question is, why do we care about forest structure? And that's demonstrated in this graph right here on the right, where we see the trends between rugosity and above net ground primary productivity. And rugosity is generally just the structural complexity of the canopy. So here we see that as the forest becomes more complex, above net primary productivity increases. And this is something that both scientists and policymakers are interested in, because it means that the more complex the forest gets, the more carbon it's able to store. And then this leads into the type of data that we are using. So working with JEDI data, which is the Global Ecosystem Dynamics Investigation. This was launched by NASA in December of 2018, and it is aboard the International Space System. And it has the main goal of collecting precise measurements of Earth to understand forest structure. A little snapshot of this can be seen right here in this graph on the right, where we see the distance along the track and the LiDAR return energy for vegetation. So here we see the ground elevation is this bottom, and then the heights of the canopy are here. And really what we're looking for are those disturbances. So this here, in between 100 and 300, could be a disturbance because we're seeing the canopy is very high, and then it dips down and then gets back up high again. Some of the specific data that we're working with are the relative height metrics, and how those are collected at a very basic level are that the system shoots down lasers to the Earth, and then they are reflected back up. And the reflected energy is used to calculate the relative height. So we have everything between RH0, which are the first return energy, and RH100, which are the last return energy, where RH0 represents the floor and RH100 is the top of the canopy. And everything else between is a proportion of the energy return. So RH50 isn't necessarily the 50% height, but is instead where 50% of the energy is returned. And then we can think of it also as RH25 isn't necessarily 25% of the height, but maybe where these little trees are, as an example. This leads into the main research questions, which are, can LiDAR be used to classify forest disturbance, and how do disturbances impact forest structure? So a little bit on our methods and data. For our actual disturbances, we collected them by looking at data sets compiled by state and federal agencies, as well as for drought, looking at satellite imagery and actually hand drawing some of those polygons. And all of our polygons are disturbances from 2017, 2018, and 2019. Because JEDI was launched in 2019, we wanted to make sure that the disturbances happened recently enough that we could actually detect those changes. And these maps here on the right show all of our data sets throughout California, where the red is fire, green is harvest, and yellow is drought-induced die-off. And in each of the areas, the lighter color is the actual disturbance, while the outer area is our control set. And what we're doing with that control set is using it that way we can actually classify whether it fell in a disturbance or fell outside of a disturbance. And as I mentioned, we are working with classifications. So the main classification algorithms that we are using are logistic regression, random forest, support vector machines, and supervised neural networks. And without going too much into how all of these algorithms work, the general flow of each one are that we input our variables, which are relative height and elevation. We then split the data into a training and testing set. After that, we fit the model with our training set. And then finally, we use that model to make predictions of the disturbance type on our test set. Before doing that classification, though, we actually needed to see if there were any trends for these algorithms to pick up on. And so to do that, we created this bar chart here, where we can compare the mean relative height across each of the disturbances. And in this, we see that the lower relative height values, so RH1 through 30, for example, are those lower canopy, while the higher RH elevations are the upper canopy. So then we want to compare and see the trends. So here we can already see, for example, fire and drought has a lot lower of that upper canopy than the control or even harvest. We also see that harvest has a little bit less of that lower canopy than our control does. And while not necessarily fire and drought are extremely different, you can already see that there's very extreme trends between fire in the control and drought in the control. So we want to see if our algorithm can pick up on those differences. And that is exactly what we did here. This is just the results of our random forest, which had the highest accuracy at 0.56%, which might not sound very high, but compared to random chance, where it would be 1 in 4, it's actually really good. And a little bit on how these results look. This is a confusion matrix, and how it works are this x-axis are all the true labels, and the y-axis are all the predicted labels. And everything on that diagonal going from the top left to the bottom right, all along here are the true predictions, and everything off of the diagonal are incorrect predictions. So we can see that out of the entire fire data set, 61% of those were correctly predicted as fire, while, for example, down here, 30% of our fire data set were incorrectly predicted as a control. And this helps, looking at this helps us to see how well our model is performing at certain metrics, aside from just looking at the overall accuracy. And it also helps us to compare and contrast different methods. So looking at that compare and contrast, we can see the different accuracies and how it performed. If we were only to look at the overall accuracy, we might think that the random forest was the best because it had an accuracy of 0.56. But the neural network had an accuracy of 0.55, which is barely worse, but we can see that it does much better correctly because the random forest was only able to predict drought correctly 27% of the time, while the neural network could 63% of the time. I think an important note to make with that also is that each method actually worked better at predicting drought than the random forest. Even the logistic regression, which is a really simple method, it was able to get 50% accuracy and predict drought with 83% accuracy. Which I think is really impressive. And then also looking at variable importance to tell us what metrics are playing the biggest role in the predictors. So here we can see that for logistic regression and the support vector machine, a lot of those lower canopy metrics are playing a really high role. Within the logistic regression, we see RH0, RH2, and RH1. And then the support vector machine, we see RH0, RH2, RH8, RH15. So all of those really low canopy are playing a big role in how the model is predicting. In contrast, the random forest has a lot of upper canopy data that's playing a role in it. So we see the RH100, RH99, RH96, those values that are becoming important for the model. With that also, we're seeing ground elevation is important for every single method, which might tell us that the ground elevation is just an important factor for each one. All right, so with that, some of the takeaways are that these relative height metrics from JEDI data can be used to characterize forest structure. We saw that with the overall accuracy and how well that they are able to, that each method are able to perform. We also saw that the different disturbance types do have a unique impact on forest structure as seen through that bar chart, where the fire and drought are having the largest impact on the upper canopy, while the harvest is impacting the lower canopy. And then finally, seeing that the classification algorithms are able to work with a greater than 50% accuracy, even at the most basic level. So going into some of the next steps, I really want to see adding in additional predictors such as vegetation indices, subdividing our disturbances by severity type, and then also adding in the difference between our disturbance polygon and the control. I'd also like to further tune the support vector machine and neural network. Right now I'm running those with the very basic scikit-learn package, but getting a little bit into fine-tuning them and specifying them for this data set. And then finally, a little bit about what I learned. So I'm actually starting my PhD in applied math this fall, and I will be focusing on machine learning. So this was able to give me a really good experience of working with machine learning firsthand, because I've gotten to read a lot about the theory, but never actually implemented it. Additionally, I was able to gain a lot of experience applying my background in math to climate change related problems, which is what I would also like to continue doing in my PhD. And then finally, just generally learning about life as a graduate student and seeing what it's like to conduct independent research. So with that, that is all I have to present. Thank you for listening, and I guess I'll open it for questions and comments.